All right, so today we're diving into the world of organic lasers. Imagine displays so thin and flexible they could roll up like a newspaper, or even lasers woven right into your clothes. We're talking cutting-edge materials science here.
Yeah.
And you know, this stuff might be closer than we think.
Yeah, it really might be. You shared a research paper with me, fresh from the Journal of Materials Chemistry C, about a new material called BPTFT that has scientists buzzing.
BPTFT. It doesn't exactly roll off the tongue, does it?
Yeah.
But hey, sometimes the most groundbreaking stuff has the most complicated names. So break it down for us. What exactly is BPTFT?
So BPTFT, it's a type of organic semiconductor, which means it can conduct electricity under certain conditions. And get this, it's made up of these building blocks called furans, diaphenes, and phenylenes, all linked together in a very specific way.
Okay, so it conducts electricity, but we're talking about lasers, right? How does that even work?
Yeah. Well, organic semiconductors can do some pretty amazing things with light, especially when it comes to lasers. Think about it. Organic electronics are already making waves with flexible smartphones and wearable sensors. BPTFT could be the key to even more amazing devices.
That's what I'm talking about. Flexible lasers. The possibilities are mind-blowing. So what makes BPTFT so special for this? Is it like some super material?
It's definitely got some superpowers. It's actually very similar to another material called BP3T, which also has potential for lasers. But here's the kicker. BPTFT has one tiny difference. A furan ring instead of a thiophene ring. You'd think that wouldn't matter much. But in the world of molecules, that small change is a game changer.
Hold on. Remind me what's so special about furan versus thiophene. It's all chemistry to me.
Think of it this way. Oxygen in furan is like a tiny but mighty organizer compared to sulfur and thiophene. It pulls everything in tighter, making the BPTFT molecules pack together more snugly and arrange themselves in a flatter, more rigid structure.
Okay, so tighter and more rigid. Why does that matter for a laser?
Well, that rigidity is key because it affects how the material interacts with light and electricity. It's like having a superhighway for light, making it easier for the material to absorb and emit light efficiently.
So it's all about how the light moves to the material. Got it. But how does BPTFT actually stack up against BP3T? Give me the rundown. Who wins in a head-to-head?
When it comes to organic lasers, BPTFT has a definite edge. First off, it's a much brighter light emitter. Scientists measure this with something called PLQY, which stands for photoluminescence quantum yield. BPTFT boasts a PLQY of 29% compared to BP3T's 24%. That means BPTFT converts more of the absorbed light into emitted light, making it a more efficient light source.
So brighter and more efficient.
Yeah.
Sounds like a win for BPTFT. What else makes it a champion laser material?
Well, picture this. BPTFT's molecules line up perfectly perpendicular to the surface they're on, like tiny soldiers standing at attention. This is ideal for something called photon confinement.
Photon confinement sounds intense.
It's all about trapping light within the material. It's like building a tiny mirrored box around the light so it can bounce around and amplify, which is exactly what you need for a laser. This arrangement of molecules in BPTFT makes it much better at confining those photons and creating that laser beam.
Wow. So BPTFT has this built-in structure that's perfect for lasers. It's like it was born to be a laser.
You could say that. And the researchers actually saw evidence of this lasing ability when they shone a specific wavelength of light onto BPTFT crystals. They observed what's known as amplified spontaneous emission, a fancy way of saying that it's behaving like a laser, though it's still in the early stages. The paper also mentioned that BPTFT has another trick up its sleeve: dual wavelength emission. That means it can emit light at two different wavelengths. And this actually depends on how thick the crystal is.
Hold on. It can change color depending on its thickness. That's wild. What's going on there?
It all comes down to the energy levels within the BPTFT molecules and how they interact with light. Imagine you have a ball rolling down a hill with multiple paths it can take. Depending on which path it takes, it will end up at a different point at the bottom.
Okay, I can picture that. So the different paths represent different energy levels.
Exactly. And the thickness of the crystal influences which path the light chooses, and therefore which color it emits.
So it's like BPTFT has this hidden talent for multicolored lasers, and it only reveals itself when the crystals are thick enough. That's pretty awesome.
It is, but there's even more to it. Those distinct emission peaks actually correspond to something called longitudinal modes in a Fabry-Perot cavity.
Okay, now you're losing me. Fabry-Perot cavity. What's that?
Think of it like a tiny echo chamber for light, with mirrors at each end. Light bounces back and forth between these mirrors, and only certain wavelengths, those that perfectly fit within the chamber, will resonate and get amplified.
So it's like a finely tuned musical instrument.
Yeah.
Where only certain notes ring out clearly.
Precisely. And these notes of light are called longitudinal modes. The fact that we see these modes in BPTFT means it can act as this echo chamber, amplifying light and making it even more suitable for lasers.
Okay, that makes sense. So BPTFT not only has these great properties, but it's also structured in a way that makes it naturally good at amplifying light. It's like a laser waiting to happen.
Exactly. But there's one more thing that makes BPTFT truly remarkable. It's not just good at emitting light, it can also act as a transistor.
Wait, hold on. It can be a laser AND, a transistor. What can't this stuff do?
Remember those tiny electronic switches that make our digital world go round? That's a transistor. And the researchers found that BPTFT can do that too. They created something called an OLET, an organic light-emitting transistor using a BPTFT crystal.
So it's a multitasker. It can both emit light, like a laser, AND, control the flow of electricity like a transistor. This material is sounding more and more like something out of a sci-fi movie.
It really is. They found that BPTFT can conduct both positive and negative charges, which is important for making efficient and versatile transistors. They even measured how easily these charges move through the material, and were impressed by the results.
Wow, this is a lot to take in. BPTFT is a laser, a transistor, and who knows what else. But let's go back to the laser part for a second. You mentioned that the researchers actually saw evidence of it acting like a laser.
Right, they observed what's called gain narrowing, which is a key characteristic of lasers. It's kind of like tuning a radio to a specific station. As you increase the energy going into the material, the range of colors it emits gets narrower and narrower, eventually becoming that super focused beam of light we know as a laser.
So that's all about getting that light to focus in on a specific wavelength.
Exactly, and they saw this gain narrowing happening in BPTFT, confirming that laser-like behavior.
That's impressive. So we've got low energy threshold, gain narrowing, narrow line width.
Yeah.
It sounds like BPTFT is passing all the laser tests with flying colors.
It really is. But remember that dual wavelength emission we talked about? Well, it turns out that the thickness of the BPTFT crystal plays a crucial role in this.
Right, you mentioned that the color could change based on thickness. What did the researchers find out about that?
They found that for thinner crystals, only one of the emission peaks, the one at 560 nanometers, was really strong. But as they made the crystals thicker, the second peak at 595 nanometers also started to lace.
So it's like BPTFT has a secret stash of different colored lasers, and it only unlocks them when the crystals are thick enough.
It's kind of like that, and it actually makes sense when you think about how light interacts with the BPTFT molecules. Remember that ball rolling down a hill with multiple paths?
Yeah, you said those different paths represent different energy levels within the molecule.
Right. So in thinner crystals, the light tends to take the express route, emitting that higher energy 560 nanometer light.
Yeah.
But as the crystal gets thicker, the light has more opportunities to interact with the material and potentially take a longer, more scenic route, emitting the lower energy 595 nanometer light.
So the thickness is like choosing between the express lane and the scenic route for the light. That's a cool way to think about it.
Exactly. It's fascinating how something as simple as the physical dimensions of the crystal can have such a big impact on the color of light it emits.
Totally.
And they also delved into the quality of these cavities, specifically by looking at something called the Q factor.
The Q factor. Is that like a measure of how good a laser cavity is?
You got it. Think of it like this. A high Q factor means the cavity is really good at storing energy, like a well-insulated thermos keeping your coffee hot for hours. A high-quality laser will have a high Q factor, meaning it can produce a narrow line width and more powerful output.
So what did they find out about BPTFT's Q factor? Is it a champion thermos holder?
They measured Q factors of around 250 to 300, which is pretty impressive, especially considering that they were using the natural facets of the BPTFT crystals as mirrors.
Natural facets? You mean they didn't have to add any special coatings or anything to create the mirrors?
Exactly. The crystal itself provided the reflective surfaces, which speaks volumes about the quality of the material. And they believed that with some clever engineering, like using specially designed mirrors. BPTFT's Q factor could be even higher.
Wow, so even in its raw form, it's already showing great potential. That's pretty incredible. Okay, so we've covered a lot of ground on BPTFT's laser skills. Low threshold gain, narrow line width, dual wavelength emission. Those Fabry-Perot modes, high Q factor, decent coherence length. It's like the ultimate laser package.
It really is shaping up to be a fantastic material for next-generation organic lasers.
But remember, it's not just a one-trick pony. BPTFT also has that incredible potential as a transistor. Let's dive into that side of things and see what the researchers discovered. What were the results of those transistor experiments?
Well, they found that BPTFT exhibits something called ambipolar charge transport, which means it can conduct both positive and negative charges. This is a valuable characteristic for transistors because it allows for more flexibility in device design and operation. You can think of it like having a two-way street for electrical current, giving you more options for controlling the flow of electricity.
Okay, so it's not just about emitting light. They could also control the flow of electricity efficiently. It really is a multi-talented material.
It is. And when they measured how quickly these charges move through the material, they were quite impressed. While the values weren't quite as high as those for BP3T, its close relative, they were still very promising, especially for an organic semiconductor.
So as we wrap up our deep dive into BPTFT, what are the big takeaways for our listener? What do you hope they walk away with?
I hope they're as excited about BPTFT as we are. It really highlights the power of molecular design. Just by swapping out one little ring in the molecule structure, scientists were able to create a material with significantly enhanced properties.
It's a good reminder that sometimes the smallest changes can have the biggest impact.
Absolutely. And BPTFT is a prime example of how these tiny tweaks can lead to huge leaps forward in technology. It's not just a cool scientific discovery, it has the potential to revolutionize the way we think about electronics.
Okay, so takeaway number one, molecular design matters. What else should our listener keep in mind?
Well, BPTFT really embodies the promise of organic electronics. These devices made from carbon-based materials offer advantages that traditional silicon-based electronics simply can't match. We're talking about flexibility, lightweight, and even biocompatibility.
So BPTFT isn't just about better lasers or transistors. It's about a whole new approach to electronics that's more sustainable and in tune with our world.
Exactly. And one final takeaway I want to emphasize is the importance of interdisciplinary collaboration. This research brought together chemists, physicists, and materials scientists, all working together to create something truly groundbreaking.
It's a beautiful example of how different fields of science can come together to solve complex problems and push the boundaries of what's possible.
Precisely. And it's this kind of collaboration that will continue to drive innovation in the years to come.
So to our listener, if you're fascinated by the future of technology and the power of material science, keep an eye on BPTFT. It's a material with a bright future, and it might just be the key to unlocking a world of incredible possibilities.
Couldn't have said it better myself.
And that brings us to the end of our deep dive into the fascinating world of BPTFT. We hope you've enjoyed this journey into the cutting edge of material science, and that you've gained a newfound appreciation for the power of these tiny molecules to shape our future.
It's been a pleasure sharing this exciting research with you and our listener.
Until next time, keep exploring, keep learning, and keep diving deep